So in this example, we're told we have a gas contained within a piston cylinder assembly. So let's just draw a little sketch of that. So we have a piston cylinder with a gas inside here. And we're told that the piston cylinder assembly undergoes two processes, A and B, between the same two end states, 1 and 2, where the pressure and volume are given and the internal energy are given at state 1, and the pressure, volume, and internal energy are given at state 2. And by the way, these pressures are given in, it says 10 bar here and 1 bar here. We'll assume that those are absolute pressures. It doesn't specify it exactly, but we'll assume they're absolute. So process A is following this, what's called a polytropic process. It's PV raised to some power. Here the power is just 1, is equal to a constant. And then process B is a constant volume process from state 1 to a pressure of 2 bar, followed by a linear pressure volume process to state 2. So one of the things we're going to do is just first sketch this on a PV diagram. So let's do that first. So here's volume on this axis, pressure on this axis. We're going to be starting at state 1, and let's put that in here. So here's state 1. That pressure is 10 bar, and the volume is 0.1 cubic meters. And then state 2, we're told, is at 1 bar and 1 cubic meter. So let's put that down here. State 2, this is 1 cubic meter and 1 bar. So path A, or process A, we're told follows this PV equals a constant relationship. So that'll look something like this. Okay, so that's path A. And then path B, or process B, we're told it's a constant volume process from state 1 to a pressure of 2 bar. So that'll go down like this. So this is 2 bar. It's a constant volume process here, so same volume. And then a linear pressure volume process to state 2. So that means it's just a straight line heading over that way. So this is process B. So that's our first part of the problem, sketch the process on a PV diagram. So we've just done that here. And then we're asked to find the work by the gas on the piston. And we'll do that for both different processes, as well as the heat transfer from the gas in both of these processes. So to find the work, what we're going to do is just going to make the gas our system. So I'll just draw a dashed line to indicate that. Let me just draw my energy flow diagram. Here's some heat coming in and work being done by. So this is Q into and work by. And we're going to calculate the work done by the gas. And it's going to be PDV work, right? What's happening here is the gas has some pressure. It's expanding or contracting against this piston. So it'll be PDV work. So it'll look like this to calculate the work. And then for process A, we know the pressure is related to the volume using this, oops, let me fix that, using this PV equals a constant process. So we can substitute in for the pressure. By the way, the constant we can find from the initial conditions. So we'll put in a P1, V1, right? So that means that P is equal to P1 times V1 all over V. And then we can substitute that into the integral. And then the P1, V1 are constants, so we can pull those outside the integral. So this will just be an integral of dV over V, which is a natural log. So in the end, this will look like the following. So that's the work done by the gas on the piston for process A. Now we know the pressure and volume for both of the states. So P1 is 10 bar. Again, it's an absolute pressure. V1 is the 0.1 cubic meters. And then V2 is the 1 cubic meter. So we can plug those numbers in, and what you'll get is the work done by the piston using process A comes out to be 230 kilojoules. So this is process A. All right, now let's calculate the heat transfer from the gas using process A. So to find the heat transfer, I'm going to make use of the first law applied to that same system of gas. So from the first law, we have the change in total energy of the system is equal to the heat energy put in via heat transfer minus the work done by the gas on the surroundings. We just calculated the work done by the gas. That was 230 kilojoules. Since it's by the way, since it's a positive value here, that means that work is being done on the surroundings by the gas, which means that the piston would be expanding. It's moving out to the right, which you can see that here as we go from state 1 to state 2, the volume is increasing. All right, so the change in total energy of the system will be the change in internal energy plus the change in kinetic energy plus the change in potential energy. And we're told in the problem statement that the kinetic and potential energy effects can be ignored. So that means we can say that these are both negligible, so they're 0. And we're left with the change in the change in internal energy, but that's given. So that delta U will be U2 minus U1. And we're given that U2 and U1. So we're told initially the internal energy is 400 kilojoules, and then at state 2, the internal energy is 200. So this will be 200. And it was initially at 400 kilojoules. Right? So then we can plug in our values. And when we do that, I'm just looking at my calculations. When we work all that out, what we'll find is the heat transfer, Q, into the gas comes out to be 30 kilojoules. All right, so that gives us, well, actually in the problem statement it says from the gas, and I did into the gas. So if you want it from the gas, it'd be out of, Q out of would be minus 30 kilojoules. That's why it's handy to have these subscripts so you know whether that's the energy going in or going out. Okay. All right, now let's do the same types of calculations for process B, where it's a constant volume and then a linear process. So to find the work, again, that's going to be PDV work. Now, in this case, I'm going to do something, the path is a little different. So the pressure varies in a different way than it did up here. Up here, for path A, we knew this PV is equal to a constant, but here the pressure varies in a different way. First of all, as we go from 1 to, let's call this point 1 prime. As we go from 1 to 1 prime, the volume remains constant. So that means there is no PDV work here because the change in volume would be 0. So really, the only PDV work being done is from 1 prime to 2. So I'm going to change this from V1 to V1 prime to V2. And then I only need to worry about how the pressure varies from 1 prime to 2. And we were told that this was linear in the problem statement, meaning that's the equation of a line. So in that case, the equation of the line, the way the pressure varies is, let me write that down off to the side here. So the pressure would be like the initial pressure, P1 prime, is equal to the slope, which would be how the pressure changes. So it'd be P2 minus P1 prime all over how the volume changes, V2 minus V1 prime, times V minus V1 prime. So that's the equation of a line. That's just describing that path there. So then when I plug in the pressure down here, it'd be P1 prime plus P2 minus P1 prime, V2 minus V1 prime in the denominator, times V minus V1 prime dV. And then the limits of integration are V1 prime to V2. Okay, so we can do that integral. Now this one's, by the way, I should be a little more careful with my parentheses. It looks like that. So this one, of course, is a little more complicated, but it's still certainly doable. And by the way, we know what P1 prime is. P1 prime is 2 bar. V1 prime is still 0.1 cubic meters. Of course, P2 and V2 are given at this point. So P2 is 1 bar, V2 is 1 cubic meter. So we can perform that integral. You just do it in a couple of different parts here. You have P1 prime times dV. That's very easy because P1 prime is a constant. And then you have this one times dV. That one's actually pretty straightforward as well. This quantity in parentheses is constant. V, that would integrate to be like a 1/2 V squared. And the minus V1 prime, that's just another constant. So that just integrates to a volume. So we can do that integral. I won't go through all the steps here just for the sake of time, but it's this is the proper setup for it. The integration is not that hard. It's just a little more tedious. But when you work it out, this work for process B comes out to be 135 kilojoules. So you'll notice that even though we're going between the same two states, state 1 and state 2, we get different amounts of work. And the reason for that is because we're taking different paths. Path A looked like that. Path B was like that. And since it's PDV work, if you look at this, it's the integral of PDV. That's equivalent to the area under the curve. This is the pressure and volume, so integral of PDV is like the area underneath these curves. So you can see, let me highlight it in yellow. Here's the amount of work done following path A. So that yellow area corresponds to this 230 kilojoules. But for path B, it's the area under this curve, which would just be this part that I'm going to highlight in green. So it's just this part. So this one is actually, the green curve has less area compared to the yellow area. So that green curve has less area, and you can see that's also reflected here, that the work is smaller than what we calculated for process A. So it all is consistent. All right, now that we have the work done using the process B, we should now calculate the heat transfer into the system for process B. So for that, we'll follow the exact same procedure up here. We'd apply the first law to the same system. We still neglect kinetic and potential energy. The change in internal energies are still the same. Since internal energy is a property, it only depends on these endpoints. It doesn't depend on the path. So it's still 200 kilojoules and 400 kilojoules. The work now, instead of being 230 kilojoules, is now 135 kilojoules. So we'd put 135 in here instead. And then we'd solve for the heat transfer. And the heat transfer following process B comes out to be minus 65 kilojoules into the gas. So that means it's actually coming out. So the Q out of would just be 65 kilojoules. Okay, so this means that there's 65 kilojoules of energy going from the gas into the surroundings. All right, so I think we've covered everything we need to on this example. The key things here are recognizing that the work done by the gas is PDV work. And to find the PDV work for process A, you just need to make use of this expression, PV equals a constant, which is what we did right up here. And that constant is just based on the initial conditions. You could also use the final conditions too. Either way, you'll get the same result. I just used the initial ones. To find the work for process B, it's a little more complex. From 1 to 1 prime, the volume doesn't change, so there's no work. From 1 prime to 2, it's a straight line, so I just made use of the equation of a line. Plug that in for our pressure down here. This integral is just more tedious. It's still not hard, but it's tedious. So you get a different amount of work, which is expected since work is path dependent. And then for both cases, to find the heat transfer, we made use of the first law, recognizing that the change in total energy in this case would just be equal to the change in internal energy, because kinetic and potential energies don't change, we're told in the problem statement. And then it's just a matter of solving for Q, knowing what the values for U1 and U2 are, as well as the calculated values for the work done by the gas. All right, we'll end the example there.